All right, in this video, we're looking at how to apply the methods of solving linear equations to equations that have fractions and decimals. So remember, we'll be using this SAM-C approach, right? Simplify, apply the addition property of equality, the multiplication property of equality, and then finally check your answer. And as always, we'll always be looking at the golden rule of algebra. Whatever we do to one side, we'll do to the other. All right, so looking at the first one, the first thing you often want to do in a problem that has fractions like this is to multiply the entire equation by the least common denominator for the fractions. The reason why you want to do this is you want to eliminate the fractions to make the work simpler for us. So what would be the LCD for the denominators in this problem, which are basically 3 and 5? Well, the LCD for 3 and 5 can be found by counting by the larger denominator, which is 5, until you find something that the smaller denominator will go into. So for example, 5, 3 doesn't go into that, then there's 10, 3 doesn't go into that, then there's 15, and of course 3 goes into 15, so that would be our least common denominator. So we can't use 5 and 10, but 15 will work. Okay, from there we're going to multiply each of our terms in the equation by that 15 LCD. So we're going to put a 15 here in the numerator and multiply that fraction by 15. We're going to do the same here for this fraction. We're also going to do the same for the x, and we're going to do the same for the 2. So in each case, we're going to put that 15 there and multiply each term in the equation. So every term, right? Not just the fractions, but everything. Whatever you do to one side, you must do to the other. So we're going to do it straight across. All right, now, if that's the case, what's the result going to be? Well, the 3 will go into the 15 5 times, giving you essentially 5 times x minus 1. Then we'll have the plus sign. 5 will go into 15 3 times, giving you 3 times 2x. Then you'll have equal to 15 times x, which is 15x, plus 15 times 2, which of course is 30. All right, from here, the next step of the process is to go to the SAM-C approach, right? So we're going to begin with simplifying, then after simplifying, we're going to do the addition property, multiplication property, and then finally check our answer. So for simplifying, we're going to distribute first and then combine like terms. So 5 times x will give you 5x, and then 5 times negative 1 is going to give you negative 5. Then we'll have plus 3 times 2x, which will give you 6x, and that'll be equal to 15x plus 30. Now on the left-hand side of the equation, we have some like terms. So let's go ahead and combine those. I have 5x's here. I have a 6x here. Together, that gives me 11x. Then we'll have our minus 5 with that, equals to 15x plus 30. Now we're going to apply the addition property of equality. So remember, we tackle those things that we can move around easily first. So what I want to do is maybe subtract 11x from both sides. And I'll do that both on the left and the right. So I'll end up with negative 5 is equal to just 4x plus 30. So the next step of the process is to continue using the addition property of equality, but this time to get rid of this 30. We don't want the 30 near the x, we want to get that away from x. So in order to do that, we need to subtract 30 from both sides. That will remove the positive 30 from the right-hand side of the equation. So I'll do minus 30 to both sides. And we'll end up having negative 35 is equal to, this cancels out, and we'll have 4x. All right, now the final step of the process is to apply the multiplication property of equality. We have 4 times x, right? And we need to do the inverse operation to get rid of the 4. The inverse of multiplication will be division. So we're going to divide by 4, divide by 4. The 4 here will cancel out, leaving you finally an answer of negative 35 over 4 is equal to x. Now, negative 35 over 4 is not the prettiest fraction in the world, but it is reduced. 35 has 7 times 5 in it, and 4 just has 2's in it, so it doesn't look like we're going to be able to simplify that any further. Okay, so we can leave that as our answer. You can check, and you probably should to be safe, but we're going to trust that we solved the problem correctly and not plug negative 35 over 4 back into that equation. You can tell that checking here would be a little bit of a headache. All right, let's take a look at example B then. Example B has decimals in the equation, and there's nothing wrong with solving equations with decimal and leaving the decimals the way they are. It's just that some people are not comfortable with decimal arithmetic, so for them they prefer to work with whole numbers. So what I would like to do then is to just eliminate those decimals. And the way we'll eliminate the decimals is actually by essentially multiplying both sides of the equation by the same thing. And that thing we multiply by has to be large enough to move the decimal place enough places to turn the numbers into whole numbers. So what you want to do is look at your decimals in the problem and say, how far would I have to move the decimal point in each term in order to make the numbers into whole numbers? Well, you can see for the first term, only moving this 2 places would give you 9t instead of 0.09t. So you'd only have to move that 2 places. Here for the 0.07, again, just 2 places is required to make that into a whole number. But to make this last one into a whole number, you'd have to move 1, 2, 3 places. So we're actually going to require that we move it 3 places for every term, because we don't have the luxury of moving it 2 places for some terms and then 3 places for other terms. We have to do the same amount of movement for every term. So if I move the final term 3 decimal places in order to turn it into a whole number, I need to do that throughout the equation. That'll be equivalent to multiplying by 1,000, but we don't need to think of it that way. We just have to think of it as, I want to get these decimals into whole numbers. If I have an equation, I'm free to move the decimal point as many places as I would like, to the right or to the left for that matter, but I need to make sure that I do it consistent throughout the problem. So remember the golden rule of algebra. Whatever you do to one side, you do to the other. So if I'm going to move the decimal point 3 places in this last term, I better do that then throughout the equation. Okay, so let's do that then. I'm going to move this decimal place 3 places, 1, 2, and then 3 is going to give me an extra space where I'll have to add a 0. So it'll be 90t, and that'll be equal to, same thing here, 1, 2, and then 3, so I'll have 70. Plus, if I go 1, 2, 3 here, I'll just get 1t or t, right? So 1t is fine. Now from here, this is a pretty easy equation to solve. We just have to apply the addition property of equality because there's nothing to simplify. So we're going to move this 1t to the other side, so I'll subtract 1t from both sides. And that'll give me 89t is equal to just 70 because these guys cancel out. And then finally, I want to get the t by itself, and that 89 is attached to t using multiplication. That's 89 times t. So to undo multiplication, I use the inverse operation, which is division. So I'm going to now apply this multiplication property of equality that says I can divide whatever I want into both sides of the equation. So I'm going to divide 89 into the left, and I'll have to do the same on the right. And then finally, we'll get t is equal to 70 over 89. Now we could try to reduce the fractions here if we wanted to, but I don't think we're going to find anything in common between these two. I don't believe that 89 is divisible by 7, and we won't get a 2 or a 5 in 89, and those are the only factors 70 has. So I think we can safely say that this fraction is already reduced as far as it can be reduced, and so our answer is 70 over 89.